This is Algebra version X. It is dedicated completely to the sine wave section on our datasheet. So first off, the frequency of sound is normally given in hertz. We're told this on the original datasheet, and it's normally referred to as F. And the number of is the number of vibrations per second. We've got an equation for a sine wave, unlikely to be given to us. But what we do have is a request to find the relationship between F and W. Now, if we look on the datasheet, we are given the information that 360 times by what is actually the frequency, which we're told here. So we've got this equals this value in the equation. So the relationship between F and W, we've got 360 times by F equals omega. Thing that looks like a W, actually omega. So if we want to find the relationship between F and W, it may well be like this. What we may be asked is to find the relationship or to find an equation for F in terms of omega. If it's phrased in this way, we need an F equals. So to get the F on its own, divide by 360. So we've got omega over 360. Okay, so second question. Use the example on page 4 of the datasheet in order to find the equations for the sine waves. So these are just the sine waves because they are a single note. So on the equation that we are given, we have this value here, and that is linked in with our maximum loudness, which is our amplitude. And we also have this value here, which is omega, and is found by 360 times the frequency. So for the different equations that we've got, we can start off with an equation being y equals. Now first comes our maximum loudness, which is our amplitude. So starts off with 70. So 70 sine, and then this bit is going to be 360 times by the frequency. And then we've got t degrees. Now they are probably going to want us to actually have worked this bit out. So we'd have ended up with y equals 70 sine brackets 105,840 t degrees. So that just comes from 360 times by the frequency. So next one, we have maximum loudness. So this is our amplitude. So we have y equals 95 sine brackets 360 times by the frequency, and that equals 158,400 t. Next one, we've got y equals our amplitude, so our maximum loudness, sine, and then 360 times by the frequency, which is, learning to count, 1, 2, 5, 6, 4, 0 t degrees. Then we've got this next one, maximum loudness A, so y equals 65, which is our amplitude from the equation that we were given on the data sheet, sine frequency times by 360, which is 105840 t degrees. Then next we have y equals amplitude, which is our maximum loudness, sine 360 times the frequency, which is 141120 t degrees. And lastly, we have y equals the amplitude, sine brackets 360 times by the frequency, which should give us 94320 t degrees. So all we're doing here is looking at the maximum loudness, which is A, the frequency, which is F, and using the equation which is on our data sheet, and that equation translates to y equals the amplitude sine. Now this section here is your frequency, which is F, so 360 times by your frequency, which is F. So that's basically just a case of going through, practicing. Amplitude goes at the beginning, 360 times your frequency. So our next section is actually looking at extracting information from the equation. So if we go with the easy bit first, the amplitude is the number at the beginning. So our amplitude in this first case is A, and that is 40. So A is 40, then amplitude is 54, 45, 20, 50, 44, and 60. So that first value is your amplitude. If you forget, you've actually kind of got it as it tells us its maximum loudness is 60. We've got that 60 in the equation, and we actually also have up here the fact that the amplitude is your maximum loudness, and that amplitude is A. Now the frequency. The frequency we've got here, and our frequency is going to be 360 times the frequency gives us the angular frequency. So to just get the frequency, we divide the angular frequency by 360. So for something like this, we've got frequency. So what we're going to want is 141120 divided by 360, and that will give us our frequency. So, first off, we've got 392. So, number divided by 360 is 247. Then 249. Big number divided by 360 is 349. Is 262. Here's 330. And then lastly is 294. Okay, so each of these frequencies corresponds to one of the notes that we've been given on the table. So this is kind of just a case of matching things up. So 392 is G4. I'm sure if you actually play music, this means a whole lot more. So 247 is B3. 249. 249 does not exist. That's because we have had a dyslexic moment and written 294. 294, however, does exist and is D4. 349 is F4. 262 is C4, which we're told is middle C on the piano. Don't know if that's going to be relevant, but has the potential to be. 330 is E4. And 294 is D4 for the second time. So it is just a case of look up the frequency that you found in the table on the datasheet. Okay, right, next thing. Find the period of this equation and of this equation. Okay, so an equation that you are supposed to be familiar with is the fact that omega is 360 divided by the period, or the period is 360 divided by omega. It's a rearranging thing. You may have seen it written almost in the way that they do the speed distance times triangles, at which point it would look like 360 omega times period and would have a little triangle around it. So if we want to find the period, we do 360 divided by omega. So 360 divided by omega in the first case is 79200, which is something fairly horrible. We also have the option of it as a fraction where it looks a little bit nicer. So our first one is 1 over 220. If we want it as a decimal, we've got this minus 3, so that means we have 3 noughts at the beginning, 0.00, and then we've got 45 that reoccurs over and over again. So we want a little reoccurring dot on both. For our second equation, we are doing 360 divided by 118800. This has the decimal option, which is 0.00 because of that minus 3, and then goes 30 and that's a bit that recurs, or we've got the option of a fraction, which is a bit more friendly. Okay, determine what musical notes they are. So determine what musical note they are. We're going to need to work out the frequency. The period that we've just done isn't going to help. So we want to know what note they are. So the period is equal to 1 over the frequency. Or at least 1 over f, where f is the musical frequency. So what this means is, especially if we've got it in this fraction, the frequency of this first one, we have a frequency of 220. So frequency is that. So our note is going to be a 3. For the second one, frequency equals 330. So the note is going to be E4. And that comes from the fact that the period is 1 over the frequency. So period being 1 over the frequency actually means that having these as fractions makes your life a lot easier, because it gives you that value there as your f. So this is where we get the two waves together. So we are adding together two waves of different frequencies, and we get a wave equation. It's not a sine wave anymore, it is a wave equation. It's not a sine wave because it doesn't go up and down in a nice, steady, even thing. It does slightly weird jumping around. We know that t is time in seconds, we know y is loudness in decibels, and we want to draw part of the wave. So what we can do is, on our calculator, start off, just double check that you are in degrees, given that's what you need to be in for the whole of the EAS. Then if we go into a table, because we want to fill out a table, if we put in the equation 40 sine, then the slightly horrible big number, which is omega x, and then we can add the second one in too. Make sure you don't forget the x, otherwise you end up with a flat line, which isn't very helpful. So if we set up our table, mine currently is going from 2 to 8, going up in ones, not massively helpful. But what I can do is, once I've got my table, I can type in my numbers, and then I will get a y value that is what I want. Because what we've got here is going up in nice jumps. We also had the option to go, we want to start at 0.0065, we want to finish at 0.0105, and we want to go up in jumps of 0.0015. So 0.0015. So when we go into our table, we should end up with 40.735. Then we've got a jump down to minus 63.03. Then we're heading back up to 43.93. 0.36. That does not make logical sense. I've done something stupid. Okay, we weren't going up in 1.5s. We're going up in 0.0005. Yeah, that makes more sense. Okay, so we have 40.74. We have 17.95. We have minus 27.66. We have minus 63.03. We have, go down one, we have minus 57.30, minus 10.63, 43.94, 66.57, and 43.735. Okay, so we can then draw the graph using these axes. Okay, drawing our graph, you'll be given a printed piece of graph paper rather than having to draw it yourself, and 90% of the time they will even give you all of your axes drawn on it. So, things that are worth doing. Looking at your graph paper, you've already got the equation in table, so you can just go across into graph and it'll draw it for you. So we are looking and expecting a graph that kind of goes like this. Now my graph, if I change the view window to the thing I'm actually plotting, my minimum x is 0.0065 and my maximum is 0.0105. So when that's drawn, this is pretty much what I should be expecting to see, assuming I haven't done anything weird. So 0.0105 from 0.00. Okay, so that looks fine. It's a slightly weird thing, but we can kind of go with that. So we've got an idea as to what it should vaguely look like. So starting off at 0.0065, we are at 40.72, so a bit under 41, 17.95 at here, so 16, 17, just a tiny bit under 18. Then we're dropping right down to 27.66. So 27.66, not quite 28. Minus 63.03. So minus 63.03. Then heading back up again, which to be fair is kind of what we expect from looking at the graph. So we've got 63.03, 57 bit, then minus 10, and it's minus 10.63. So then we've got 43.94, so 43.94 3.94, then 66 at 10, so 66.5, and then back down again to 43.7. So we've got the beginnings of our curve. Other bits that we're going to need to make sure that we've plotted correctly are your maximum point, once it's thought about it. So we have a maximum at y equals 66.58, and that's at 0.00998. So 66. So basically this bit. And our minimum is at minus 66.5, which is kind of what we'd expect. And that happens at 8.1. So that is minus 66.5. So this one here is our actual minimum point, which we would have missed out if we'd just been doing it from the points we've been asked to plot. So we are expecting a fairly smooth curve running between all of our points with the normal no double lines. So we should be heading down here. Nice smooth curve over the top. It may well be useful to find out where your roots are, so we know where we're going through. So going through at 7.2, yeah, pretty close. Coming back up through 9. .009 and a tiny bit. So coming up through here, going through our maximum, and then we can stop there. So should have a thing that looks a bit like this. Okay, so use your graph to find the gradient. Now, depending on your knowledge of your calculator, this gradient at this point. So, if you're an A2 student retaking your AS, you can use calculus if you're good enough. But realistically, it makes sense to do this using a tangent and a straight line. One thing that is worth doing is, if you can turn on your derivative function, then what you will find is, if you do gsolve ycal when x is 0.007, it will tell you not just what your points are, but maybe it's in table then. Or did I just turn the derivative off? Nope, derivative. So you can go 0.007, and this column here, this third column, will give you your derivative. So you are expecting a gradient that is about minus 76453, at least to do 3 significant figures. So that gives you a fairly good guess as to what you're expecting. So if you come back to your graph, you can find where 0.07 is, then draw a tangent at that point. Tangent is a line, so it will require a ruler or something equally kind of straight. Okay, so looking to find the gradient, we've drawn our line of best fit, and then we've got from our calculator what the gradient actually is. So, doing it the official way that we're going to need to, we can choose 2 points on our line. So our first point is 0.0065 and 64. And then if we come a decent distance away, what we can do is, if we take this one, then we've got an x coordinate of 0.0071 because it's just past the line, and a y coordinate of minus 24. So, using calculator, we've got gradient is so m equals y2 take y1 over x2 take x1. So using brackets, we've got 64 take away, nope, we've got minus 24 take away 64 as our y coordinates. No, concentrate. We've got minus 24 take away 64 as our y coordinates, and we had y2 at 0.00. No, that really isn't that. That is at 6, because it's 1 past the 5, not 1 past the 7. Yeah, that's fine. 7, 6 minus 0.00. And this is why you don't let dyslexics get tired before typing things. Right, 64 gives us minus 88 on the top, and then gives us, divided by brackets, 0.0076 take 0.0065, and that gives us 8.0076 take 0.00. So that is minus 8 4 zeros. Now, these two feel quite far apart. However, if we look at it from the point of view of percentage error, we'd have 1, 2, 3, 4 take 453 divided by our actual value that we were supposed to have got. Actually, we're looking at less than 5% error. So less than 5% error is kind of workable with. So we'll take that. So what this tells us, on our axes, we had time in seconds and we had loudness in decibels. So our gradient tells us that for every second, the loudness falls by 8, 1, 2, 3, 4, and decibels is a little d and a capital B. So x-axis was in seconds, so each additional second loudness is falling by this absolutely massive amount compared to the like 60s and 70s we've actually got on our axis, but then we are dealing here in hundredths of seconds, so actually it's kind of okay. Right, so Stella, still our music student from the datasheet. Different two waves. So we've got a wave with 50 amplitude and a wave of 25. And then they've got these values of omega. And we're asked to sketch the resulting wave. So a sketch is a little bit different to plotting it because all we actually need is our key points. So if we exit that and put in a new one, we have 50 sine brackets 79200 x, and then if we group that together, then we've got 25 sine 158400 x. So we've got a slightly weirder graph, but it is a lot more regular. So we've got maximum point, weird wiggle, minimum point, maximum point, weird wiggle, minimum point. So if we are sketching the resulting wave, we are going to need to know certain things. We're going to need to know what the roots are. So we've got 1 at 0, 0. Then, after a little bit of a think, we've got 1 at 0.00227. Then our next one is a tiny little bit further along. And then we've got a third one crossing again once it's thought about it for a bit at our next point. So we've got our period and we've got this kind of weird wiggle in the middle. So it almost looks as though it's flattened out in this area here. So it may well be worthwhile to see if we can zoom in to have a look at what is happening here. So if we condense our graph and zoom it to one of the periods, so we've got, exit that a second, that can go up to 0.0045, which I think is roughly speaking where we're going. So we've still got this slightly weird section here that kind of looks flat. So what about if we view window and go, actually, don't want to go from 70 to 70. If we just go from -10 up to 10, that way we can have a much better look at what's happening here. And realistically, still just looks kind of flat. So if we zoom in again, then we can have a look and we'll go from -1 to 1. And what we've got here still looks kind of flat. So if we come back out to the original size that we were looking at, assuming our graph is going to need to go from minimum of -75 up to 75. We can sketch this. So we are going to need to start at 0, we go up, we kind of do weird flatteny thing, we go down and then we go up again. Apologies for the graph drawing, really poor at sketching. So if we then look, we've got G sub max, that is this point here, and that is looking at 64.9. And we've then got an X value there, only that won't actually be 0.9 because of rounding. That will push that up to 65.0. Then this one is therefore going to be minus 65.0. So we've then got -4 So this point here is going to be 0.1237558. And then we've got the next one across. Doesn't like that. Menu, draw it again. Then we've got our middle value here, which is g sub root, and that can go across. So this one we are looking at so this point here is 0.00227. And then our next one, we can do G-solve minimum, and that's going to give us, once it's thought about it for a bit, a minimum, which was what we thought, and 3.76, so that one is 0.0037. And then that 8 is going to round up to a 9. So we want to know where this wave is changing fastest. Now, that's going to be at a point that we can see either going up or coming down. At the moment, we're just looking for change. So if we do a view window and we take that all the way up to 0.006, what we've got is something that's going up, flattening off, coming down, flattening off, going up. But this section here is getting faster and faster and faster. So the time that it's going to be going or changing fastest is at the end of the first period, and to be fair, the beginning of the first period. So wave is going to be changing fastest at actually 0 seconds and first period. So what y value is the wave changing fastest? It's actually changing fastest at 0 decibels. Time it first occurs is 0 seconds. Then what notes were combined? So the notes, if we're looking for those, we are going to need to use our omega value. So we can do that with omega equals 360 of the frequency. So our frequency is going to be our omega value over 360. So menu is 79200 divided by 360 gives us 220. And if we look on our data sheet, which, no, that's not there anymore, which if we look on our data sheet gives us, hidden underneath, the note of a 3. So that's going to be a 3. And the second one, when we look at it, if we do that, is 1584400, and that divided by 360 clearly means I've typed it in wrong. That's because I put 2 4s in it. 158,400 divided by 360 is 400. So our second note is that 440, which is a 4. So the reason this might, no, A4. So the reason this might produce a distinctive wave is because they are both A. So what you're looking at is something that is 1 octave apart. So both notes are A, comma, just an octave apart. So it kind of makes sense that if you've got two A's, then they might make, or they will have a frequency that balances out in the middle, which is what creates this weird flat bit. So, transformations. This was slightly mean, but to be fair, I'd rather you saw something mean on a data sheet than in reality on an exam. So, transformations that take you from 50 to 25. So that's going to be a stretch. And if you're stretching something from 50 to 25, it'll be scale factor times by a half, and that's in your y direction. And the other bit is our x, so we are going from this one to this one. So to go from this number to this number, you would times by 2. So because we are looking at something that is in the brackets with the x, it will do the opposite of what you expect. So we end up with a stretch scale factor, not 2, but divide by 2, and that's also a half, and that is in your x direction. So to go from 50, so amplitude to amplitude, normally we don't have a number here, so it's just going to the 25, but here we're starting, so we're dividing by 2. Here, what we want to do is multiply it by 2, so the scale factor stretch is going to be half.